Good afternoon, everyone. Our today's speaker is Jakub Kolar. Kolar, is it fine?
Yes.
From Brno, from Masaryk University. Jakub is a final year PhD student there, working on variable stars and also using some databases of variable stars using OGLE, or in Spanish to OGLE. And he will tell us about doubly eclipsing quadruple systems. So the floor is yours.
Thank you very much for this nice introduction, and thank you all to be here. As Milena said already, I will be talking about quadruple systems, especially so-called doubly eclipsing. So first of all, I would like to introduce you the quadruple stars, then something about the detection of these objects. Then I will talk about our research of the individual candidates and also some, let's say, proper or global statistics of the periods and resonances. Generally, when we are talking about stars, sometimes we mean single stars, but maybe also binaries or some higher multiples like triple stars, quadruple stars, and so on. And when we have these stars together, like 3 or 4 or more stars, we always need some physics behind the binaries because we always have some let's say stellar pairs or some couples. Probably the most simple multiple except the binary is the triple star. And here there is a stable solution only when you have this inner binary and some, let's say, more distant additional component. And all of these three stars orbit their common center of mass. So this inner binary plus the third component orbit their common center of mass. When we have even more stars, like 4 stars together, there are 2 possibilities how to get some stable configurations. One of them is that we have this triple star and also some more additional component, which is this, the 3+1 configuration. But maybe the more known stable solution is when you have two binaries. It should be also some let's say selection effect, but nowadays we know about 3 or 4 times more these quadruples with the 2+2 configuration than with the 3+1. When we want to have even more stars, like here, the sextuple star, we always need some let's say couples or some patterns showing here. So binaries or some binary with additional component. And for this star, a very interesting star, we have together six components with this configuration where we have inner quadruple plus some outer binary. So in total, it is a system with 3 binaries, and all of these 3 binaries are also eclipsing, and we can measure them. But let's stay with these 4 stars in one system. For the 2+2 quadruples, we can define the binaries as a pair A and pair B. Both of these binaries have their inner orbital periods, and also they have their common orbit and some, let's say outer period. So usually the period of this mutual motion around their common center of mass is very long. It could be something, I don't know, even decades of years, maybe even hundreds of years. Yeah, it's quite a while. If we are lucky, both of these binaries can be also the eclipsing ones. And then we can observe two sources of variability, two sources of eclipses, and this is basically the term of a doubly eclipsing system. So this is the topic of my PhD thesis and our research, the quadruple systems with the two eclipsing binaries. One of my favorite examples I sometimes showing is this star BG int and its TESS light curve. This star or this object is known, I don't know, maybe 60 or 70 years as an eclipsing binary. And here you can clearly see that there is some large variation of the signal. But now in test data, we can see also something else. Like here, some other very small dimmings, but these dimmings are very regular with some period. And when we subtract the already known binary, when we disentangle these two signals, we can obtain something like this. So this is already known binary, and this is what remains. Something another, some new eclipsing binary. In fact, this is this period of this pair it's quite short. Yeah, only about half day. But because of the low amplitudes, no one knows before the test that we have something like this in this object. So we know this system for 60 or 70 years, and just now we can say that we know probably one of the most essential things: how many stars we have in the system. And this is probably the reason we have like TESS and OGLE and other surveys, and nowadays we can detect many more of these candidates. Let's say maybe the beginning of this research started in 2019, when we have around roughly 150 candidates. Last year, it was almost 1,000 of them. Probably this year will be a little bit more. But we need to be careful about this, because I'm referred only as candidates, not the confirmed quadruples. In fact, we have something around 70 already confirmed quadruples with this 2+2 configuration. And the rest, the most of them are still only the candidates. I cannot say properly how many, but some of them could be only a blend. That means that we have two independent binaries, but they have nothing in common. Yeah, only the same or roughly the same direction where we observe them, but they are not together in some gravitational bound in quadruple system. It is only a blend. And we need to avoid these blends and confirm the candidates as a quadruple star. It is not so easy task because how can we do it? These two binaries orbit their common center of mass, so we need to see both of the binaries orbiting, but usually these mutual motions are very long, and even if we have some long time set, like I don't know, 20-30 years, it's still sometimes not enough to see some variations or some signs of this motion. So it is in fact a task for very long time. This is the actual sky distribution. Not all of them, not all of the candidates. This is from our publication, but there is probably vast majority of them. It's around 800. Yeah, so vast majority of them is it's here. You can see here that most of them, around 80% of them, is in our galaxy and going through the galactic plane. But we have also here large and small Magellanic clouds. In fact, in 2019, most of the known candidates were in large Magellanic cloud because of OGLE and paper of Petrzaše. But nowadays, with other surveys like TESS, maybe ZTF, and also others, we have more in our galaxy. How can we detect these candidates? How can we say I have found some new candidates for quadruple star? Probably in papers or some lectures, I always hear that the most straightforward way how to do it is photometric. It is probably much easy to obtain some light curve than, let's say, high quality spectra and other sources of data. So we will use photometry. One night observation is definitely not enough. Usually we can say it's general task for every object. In this example, you have here shown the light curves of both of the pairs separately. So this is one of the pairs. This is the second one, but this is not what we observe, at least at the beginning. When we do the observation, we will observe this one, the merger of these two signals together. And when you have something like this, you can, and you know nothing else about the star, you can probably say there is some maybe trend or asymmetry in your data, and there is also some minimum. But here, when we see carefully, this time of the minimum is not exactly where is the time of the minimum of any of these pairs. It is only some strange merger of the eclipses, but it is not the real minimum actually. So when we have only this observation, we cannot say much. We cannot say practically anything. So what we need is long-term monitoring, more nights definitely, and probably some high cadence and high quality data. Still, if we use only one source of these data, we still can miss some important things. So the best way is a combination of more sources, as many as possible, and also using our own new observations. There could be several cases. How can we miss the second pair? Usually we know one of the eclipsing binaries, and we are trying to find some additional signal from these prediction. These white areas is where is the night, and what can we observe. And even if we observe all of these nights, probably it's not so easy to detect there is something else with very low amplitudes. Yeah, so still we need some more data. And also when we have some long periods, you probably observe only the part of the light curve where the eclipses are. And not the constant phase. So the long periods can also lead to miss another signal. This way can be solved by TESS because TESS has continuous data for, let's say, maybe 27. Usually 25, 24 days, and also has usually more sectors. So we have many data sets with the continuous data. That's really good. And you can see quite clearly that there are some two, maybe three signals, and sometimes we can also see some merger of the minima. Yeah. There are unfortunately also many disadvantages of TESS. One of them is it has very poor resolution. Yeah, the angular resolution is very bad, and also sometimes it has some large trends. In this light curve, it is especially in these parts, here and here. It is not some physical property, it is the instrumental error of the satellite. Yeah, but we have some methods how to determine the light curve, and also how to disentangle both pairs to have only pair A and only pair B. Usually we are doing some iteration processes to fit one of the pairs, fit the phase curve, and subtract it, and do this procedure until we're quite happy with the result. So this is the same data set. This is the same like this, but here we have the binaries disentangled. So this is pair A with its eclipses, and this is pair B, and also it is the trended. Now we can do some further analysis. We can do the minima timings. We can do some physical modeling. Besides TESS, there are also other photometric surveys, and maybe I can say there is disadvantage of the TESS. Other surveys have big advantages. For example, the OGLE, you can see here the resolution is really good against the TESS. Also there is a map on the web page, so we can be, let's say, more sure what we actually observe if there are no additional stars we don't want to have in our map. And also we don't have, let's say, continuous data, but still probably we have a longer time of observations, and when we do the faithful light curve, we can still detect some say more sources of variations. Here you can probably see that there is some known binary, but there are also some points they are through the whole light curve, but mainly they are here, or mainly they are visible here out of the eclipses, like in this region and this region. And these are also some eclipses, yeah. So even using not, let's say, so continuous data, but long-term observations, we can still detect some new candidates. All of these things are really nice and very useful. We have, let's say, almost 1,000 of candidates, and now we need to do also something else, because we need to be sure what is the object exactly. We need to confirm it is a quadruple star, and maybe do some let's say statistics of these objects. And this is what we are doing in our observing and research group called Squadra. You can see here the members. We have academics from the Masaryk University, also students, mainly bachelor and master students, and also we have the citizen observers. In fact, in the Czech Republic, we have a quite large network of Czech observers, Czech citizen observers, and they have quite, let's say, professional technique like CMOS or CCD cameras, quite large telescopes, and they can provide us very nice and high quality data. So from our point of view, it is a great disadvantage to have also citizen observers. We're doing mostly photometry. We're also trying some other things like spectral energy distribution and some spectroscopic observations. But usually we don't have telescopes to do the spectroscopy, at least for all of our candidates. So we're mainly doing photometry. And we're also doing some further collaborations, mostly maybe with other Czech astronomers, but also with colleagues from abroad. These are our two telescopes in the Czech Republic. This is the 60 centimeter in Brno, and this is a relatively new telescope, 80 centimeter in Ždánice, which is village near Brno, but there are quite nice astronomical conditions, better than in the city. And in total, our diameters are in this range. We have also very small telescope, but also quite large ones. So these two are from the Czech Republic. We have also another in the South Africa at the Boyden Observatory, where nowadays mostly students observe. And our very new telescopes are in Chile, half meter when we are doing photometry, and 1.5 meter platospec for spectra. In our set, we have roughly around 90 systems, also in northern and southern hemisphere. We are not doing fully all of them. For some of them, we're doing only some collaboration with other colleagues, but for some of them, we are doing fully research. Most of our objects are quite faint. Let's say that the brightest ones are around 9-10 magnitudes, but usually they are fainter. Maybe because of that, they usually don't have some pretty names, let's say. Usually they have some catalog or coordinates names. Yeah, so I will probably use these abbreviations like S means star, number, and constellation. Yeah, so I will mean these names we are using, but I can also send you some proper official names. We have, in fact, some new confirmed quadruples, and let's say some suspicious. These numbers can vary. It depends what you consider as confirmed or suspicious, but let's say we have around 10 of them. And now about the individual systems, I will probably start with the negative result, actually. Here in Andromeda, we have this object. You can see here the disentangled light curves, and it looks quite nice, yeah. But when we see the maps of this object, so here we have the TESS map and TESS data, and this is our observation. And this is I said already, the TESS has very poor angular resolution. And here you can see that there is probably some deformation. It's not the circular shape, but we cannot say exactly what we observe there. But when we use some other techniques and other surveys or our own observations, we can resolve these two objects as two binaries. And also Gaia can resolve these stars, and the distances between them, or distances to us, is very different. So we think that this is probably not the case of the quadruple star, and it is only a blend. Now about some, let's say, more positive results. how can we confirm that the candidate is really a quadruple star? We usually derive the minima and timings of the minima and try to see the O-C diagrams and how the O-C diagrams look like. And what we should see is the lifetime travel effect. Basically, it is something that when we have probably, let's say, this binary, it goes on this trajectory, and the distance to us is changing. And during this, the light needs, in this case, I showed our O-C diagram. When we are here, the light needs a little bit shorter time to reach us, so the minima will occur a little bit earlier. That means in this part, when the binary is somewhere here, the light needs a little bit more time to reach us, and thus the eclipsing or the minima will occur a little bit later. Yeah, so this is what we should obtain for this one, for this binary, and for the second one we should obtain something very similar, practically the same, but in the opposite way because of the orbit. So we should see for both of the binaries something like this. Yeah, this is just some example, but this is what we can expect. And these are our data. Yeah. Maybe also some note here that the amplitudes of the lifetime travel effect can say something about the mass ratio, because when we do the ratio of these amplitudes, we can directly have the mass ratio, which is in fact quite a strong tool when we use only photometry for a long time, and we can observe the mass ratio, not of the individual stars, but the mass ratio of the binaries. But it's still quite useful. And this is one of our systems. We cannot say too much about the orbit right now, but we can consider this system as confirmed. But the period we have by our modeling something 12 years, but it's still not so certain. We also did the physical modeling of both pairs. Both of the binaries are consist of let's say cool stars. Yes. Here the lifetime travel effect is quite nicely seen. We can be, let's say, sure about the period, or at least more sure than the first case. And we also did the modeling from these results. Maybe the most interesting things are the periods. You can see here, this is probably 1 day or close to 1 day. Yeah. And from the observer's point of view, it is absolute disaster to observe this star, because you always see the same thing. Yeah, you want to measure this whole light curve, but you always see, let's say, some this part. Yeah, and you need to wait several weeks to observe the whole light curve, maybe several months. Yeah. Also, the pair A period is roughly around 1 day. It is better, but still not so good. Yeah. So this is probably not so easy task to obtain the whole light curve, and the TESS data are very useful, or some other service. As an example, there are two nights of observation of this object. This is the eclipsing of pair B, and it goes to the eclipsing of pair A. So here the minimum of pair B is in this Julian date, I don't know, 0.36 maybe, and the next night it's like 0.35. Yeah, so we have basically always the same here from this pair. Yeah, and it will take some weeks, maybe months, to observe the another eclipse. Also, a system like this, when we don't know exactly what we can expect or what we have here, because on the pair B there could be some probably period changing, but we cannot be so sure yet. And here maybe also, but in the different way, and it's not the same thing. So we cannot say much yet about this object. But we can also do the modeling. We have quite nice light curves of these, and also we have usually quite cool stars. Yeah, but it depends. Yeah, I don't want to state something that there are probably only cool stars, because we don't do the models for all of them, but only let's say 20, 30. Yeah, so we cannot say this. As I said, we have also students in our group. Our bachelor student Anna Richterková did this star with very special resonance of 7-2 between the periods. The curves are quite different, but the periods are in this resonance. And also Sabina Pačková did this star. And there is some interesting thing, that the magnitude is quite faint. It is around 15 magnitudes, but still it is visible in TESS data. Yeah, probably the original intent of TESS data was around 12 or 13 magnitudes, but you can still observe 15. It is okay relatively. It has quite large scatter, but when you have large amplitudes of your signal, it is still possible. Yes, and the last one of our stars I want to show you. Maybe here the most interesting part is the O-C. From these variations, we can say it is confirmed quadruple, but mainly maybe you can see it's not so pretty. The models are not so good. And we still don't know what it could be precisely. When we do the residuals, we can obtain something like this from pair A, and it maybe look like that should be something else, some new already unknown star. And if it is correct, we have another lifetime travel effect with shorter period than our original models, our original fits. And that would mean that we have a quintuple star, and another system should be, according to the lifetime travel effect period, it should be somewhere in the system, within the quadruple star. So in our theory, we could have a triple star and also some let's say outer binary. but it still needs to be confirmed as a sure thing. And the last part of my talk will be about the periods of these candidates, mostly about the inner periods, because the outer periods are known only for several of them, and we know only the shortest ones, like several years. So we cannot do much, at least yet. But the inner periods of these binaries are quite well defined. So we can do some statistics about them. What is in this topic quite a question is what is the period ratio of these binaries and how the distribution of this period ratio looks like. Also, another task is to see if there are some resonances, if there are some, let's say, stable solutions, some stable resonant values, or maybe, on the other hand, unstable resonances. So firstly, we did the period ratio of the two binaries in the candidate. To have some order, we always do longer over the shorter one. So that means that our period ratio R was always bigger than 1, or precisely 1 where the periods are the same. And we did the distribution of these data. It's good, yes, but now we need also to have something in comparison. So we did some simulations, assuming the uniform periods, the distribution of uniform periods, and simulated this distribution for our sample of 800 systems. This was one of the simulation, and we repeated this simulation for 500,000 times to obtain some, let's say, statistically robust model. And this was our prediction. Our results are shown here. You have here on x-axis the period ratio. We're starting with the value 1, where the ratio, where the binaries have the same periods. And our maximum was 5, where we have at least some data. And here is number of systems. The blue histogram is our data, and the red curve is our predicted model. From the statistics, we can say that these two things correspond to each other. It is within the statistic the same thing. Maybe there are some small deviations, but still the sample is not so large to be sure. If there are some properties, probably when if we have more stars, deviation will be missed, or it would be better with the model. So the ratio behaves mostly as we can expect. And now the question is there some, let's say, more preferred value, some resonance which is more preferred or maybe unpreferred? So we tried to also have statistics of these resonances. From this histogram, the bins are too wide, so we need to take only a small range of this period ratio. But firstly, we need to define what is still close enough to be considered as a resonance, and what is just too far to be resonance. Generally, it's not the only task for quadruple stars. It is sometimes tricky to say this value is still close to some resonance or it is too far away. So we defined a parameter C called closeness by this equation. It is the period ratio divided by the resonance, and we took only the decimal part. As an instance, we have here some star or some object that we have the ratio 1.51. So it could be close to 1.50 resonance. And when we divide these numbers and take only the decimal part, this is what we can have. Yeah. Usually we use the percentage, so it is 0.67% of closeness to this resonance. And now, when we try to study some, let's say, properties or some phenomena, we need to have large enough amount of the systems, and on the other hand, we need to have our range of the closeness parameter too large, because some possible phenomena can be just in the scatter, yeah, and so we cannot have so wide range, and also, let's say, so small range. Thus, we took two ranges within 1% of closeness and within 2% for comparison. Let's begin with the larger or the wider range. So we have the resonances. We took integers, half integers, and also these third values. And again, here we have number of systems. The first columns are our observations, our data, and the second ones are our prediction, the simulation. And we compare these two things. You can see here probably that 1:1 ratio when the periods are the same. It's surprisingly already the same. Yeah. Maybe some deviations here and here, and the large overabundance is in the 3:2 ratio, which is probably the most discussed resonance. I think it doesn't have some proper theory, but there are some signs, let's say, that the 3:2 resonance can be some possible stable solution for these systems. We can also see something similar in the exoplanets, but probably there are some different processes how to reach the resonant values. Yeah, and we need some proper statistics and proper theory to say it clearly. But still, this is the most overabundance here and the biggest difference compared to our model. When we do a shorter range of the closeness parameter, still the 3:2 ratio is clearly visible as the most difference and the quite large overabundance here. And the others, especially, let's say, this first half of the resonant diagram, where we have at least some data, some large portion of data, you can see it's roughly the same compared to our model, but here on this 3:2 resonant ratio, we have this peak. Yeah, and it is quite similar with both of the ranges here and also here. So from this sample of 800 candidates, we can say that the distribution of the period ratio behaves as expected mostly. And when we compare our model with the data and see the resonances, 1:1 ratio is practically the same. 3:2 ratio could be some, let's say, slightly preferred option. And the 2:1 ratio, there is some decrease, but we still we cannot be still so sure. Yeah, but we can observe some decrease. So our searching continues. Hopefully, we will have some more systems. In the best way, we need, let's say, not only like some 50 or 100 more systems. The statistics will be probably roughly the same. Yeah, we need like 3,000, 4,000 of them to obtain some new properties and new results. So to summarize this talk, the doubly eclipsing systems are the quadruple stars with the 2+2 structure with 2 binaries, and both of them are eclipsing. Nowadays, we have something around 1,000 of candidates. We already confirmed some new ones, and hopefully we will also confirm others. So let's say we probably this year we can have something around almost 100 of confirmed quadruples, which is still not so good, but at least something. And from our period statistics, the period ratio distribution is as we can expect, and maybe some possible preference of 3:2 resonance. Thank you for your attention and dziękuję bardzo.
That's my check. Thank you. Any questions or comments? Yeah.
So most of your candidates contain the main sequence stars, yes?
Pardon?
Most of your candidates contain main sequence stars.
Yes, yes.
So you cannot say much about the age of the system.
This is also some of the questions, but we need to firstly model all of these stars. Yeah. Usually we don't have spectra, or let's say high quality spectra. So and other data, yeah, it's like 15, 16 magnitudes. Yeah. So we need to firstly have this information, yeah, about the age. But it is quite complicated to obtain it. Yeah. But when we have it, it would be very nice to do some distribution of this. Yeah.
You have an example of stars with hot components. Could you go to this slide?
Yeah, sorry. It's take some time. Yeah, probably this one.
Okay, and how you obtain your temperature?
Yeah, about the temperatures, because you see let's say one light or one object. So it is quite difficult to say what is the temperature of this. There are some, let's say, catalog values of maybe TESS or Gaia, but there are many things like the extinction, like the distance and other things, and it's quite complicated to rely on these values. So what we are doing mainly is the spectral energy distribution, and also we need to take account the extinction and the extinction in the different distance. Yeah, not the extinction in the whole direction, but we need to take the distance where how star exactly is. So there is also a parameter we need to know the distance exactly. Yeah. Then when we do the SED, we have the temperature of all stars, of all stars together, and this temperature is, let's say, some our upper limit for the temperatures of the stars. And now we need to estimate from the light pair shapes and maybe the amplitudes and other things of both pairs, how the temperatures can look like. So mainly from the spectral energy distribution, but there are many let's say variable parameters we need to know. The best thing is that we have spectra and we can see all of the 4 stars. Yeah, but this is not the usual case.
I was wondering about this, especially this on the right, because these temperatures are quite high for these short periods.
Yeah, I'm not sure if the temperatures are not here a little bit overabundant. I will check it. Yeah, because I remember I recently, a few days ago, I did some new models, so maybe the temperatures here are a little bit overabundant.
So following the question about this, Alec, you had something?
Yeah, I have a question, not about that, so if you want to ask about. You discussed mostly how you verify those systems, but like, what's the general goal of all these projects? After, let's say, you confirm, I don't know, let's say half of those systems with 500 quadruples, what's then? What's the scientific question you want to answer?
Maybe one of them could be how many of let's say multiples are actually in the universe, because like 6 years ago we don't know most of them, and nowadays we can see 1,000 of them. So let's say some distribution of the multiples, that could be one thing. And also maybe the statistics of the periods can be also one of the main goals.
So when you take a look at this light curves that you have, for example, from TESS, that is a big database, have you seen any changes, for example, of inclination of those systems, like some changing shapes of eclipses or anything like this? Any additional effects, or you rather try to focus on those that don't have this?
Sometimes, but usually in our data sets we don't have the inclination changes. But there are also some quadruples with this. Yeah, I think Petr Zaše has 1 or 2. I'm not sure yet, exactly. Yeah, but there are also with the change of inclination. And these could be a little bit unstable. In fact, yeah, the best thing when we have coplanar system, and this is the way this is the system when we can probably expect some resonance.
With this, everywhere you assume that these systems are attached, right?
Not exactly. No, there could be also semi-detach or contact. And there is some other variable, the period change of the contact system, which could also let's say break the resonance or some stable solution.
Anyone else? I
don't see any question from me.
Okay, so thank you, Jakub. So let's thank our speaker again.
Thank you.
Next week, we have another special guest. It's a dean of the archaeology department, and it's going to be talk about the Mesopotamian roots of astrology. Because the guy is actually an expert in archaeology or archaeoastrology. I don't know. Yeah. And the notebook is somewhere there. So please fill your name. Say thank you. You live it, yes.